Hi everyone, thank you for having me. For those of you who weren't here yesterday, my name is Rex Douglas. I direct the Machine Learning for Social Science Lab at UCSD. I'm going to be presenting work that's co-authored with Kristen Harkness, who's at University of St. Andrews right now. This work is based on a paper that's gotten through the review process and is provisionally accepted as of next Tuesday with edits, so this is provisionally a good idea. There'll be replication code and hopefully a package eventually, and this talk's going to be a little bit longer than some of the other ones, but it's also going to miss a lot of detail, so look for the paper and look for the code following provisional acceptance. The problem that I'll be tackling is georeferencing. And we often care, the reason we care about this problem is we often care about the where of events. Which village did an attack happen in? What town was a well built in? Which country did Trump insult today? We want to be able to relate things that happen to the places where those things happen. Unfortunately, there are many possible ways to describe a where using natural language text, which I'm sure you're very aware of. It turns out there are also many possible ways to describe a where and other things like maps or databases or coordinate systems. And it turns out there are lots of possible ways to try to map the two. To give you a concrete example here, here's a town in Kenya, Ol Kalou. This is a latent real life place. Here's a satellite map of it. People live there, there are buildings. It's not just a row in a data set. It's unfortunately also a row in lots of data sets. Here are 10 examples from an events data set that I'm going to be talking about today, of all about the same place or related places to it. Here's 38 examples of the same place from a news corpus from Kenya. And here are six references, 6 matches from 13 different gazetteers that we put together covering this area. And so we need some logic to be able to match true connections between real-world latent places and these kind of fictionalized representations that we have in different data sets so that we can merge different pieces of information and geolocate and actually put ideas to a specific latitude and longitude. I'm going to be making a specific argument today, which is that how you georeference matters. At least in political science, researchers rarely explain or test their georeferencing strategy. It's not a sexy topic. It's considered kind of a computer science-y issue. It usually just gets relegated to the statistical appendix online, if at all. And when you go look at that area, it's usually something about, we had undergrads look it up on Google Maps. It's not very systematic. It's not very well explained. And it turns out there are lots of different decisions and strategies for georeferencing, and some of these decisions turn out to be really subtle in ways that you don't really expect going into it. We argue that those strategies ought to be empirically evaluated. Just like any other part of a statistical analysis, there should be ideas about robustness checks and empirically validating the assumptions which you're using in your analysis. We're going to suggest some criteria and some kind of best practices that you could use to judge the accuracy and the effectiveness of different georeferencing strategies. We design an experiment to test those using real-world data, and we show that different strategies have different results. And it actually matters. And then we propose kind of a unique strategy, an ensemble method that tries to combine the best parts of different strategies and minimize the weaknesses of those as kind of a way forward for researchers. Just as a roadmap, first I'm going to introduce some new ground truth data, a new event data set that we created. I'm going to give you some empirical motivation for how we would typically write a paper in political science using that data. Some of the georeferencing challenges, some of the georeferencing decisions, introduce our ensemble approach, give you some criteria and diagnostics by which to judge it in comparison to other strategies, and then I'm going to conclude with some future directions. This is the new data set that we introduced in this paper. We've been working on it for about 4 or 5 years now. It is a micro-level Civil War conflict data set. The specific case is a colonial rebellion called the Mau Mau Rebellion in the 1950s in Kenya against the British. It was an ethnic rebellion, 3 major tribes, the Kikuyu, the Embu, and the Meru. It's an example of a government victory, and it's also an example of what's considered kind of the hard counterinsurgency, a very brutal government crackdown. It's often put forward as an example of harsh counterinsurgency methods working. So it's an important case to kind of think about rigorously, because in the qualitative literature, at least, it's kind of considered a good example of why you should crack down in counterinsurgencies. We only know a lot about it because the British kept records and hid them for a really long time, and then there was a lawsuit against the former colonial government that was dissolved on behalf of citizens that were tortured during the conflict, the actual rebels and innocent civilians during the conflict. And because of that lawsuit, the discovery process of lawsuit revealed the documents. And the National Archives and Kew in the UK were forced to put the documents out in the public. We found out about it maybe a month after they were made public. We digitized over 20,000 pages. We created an ontology and a coding scheme to transfer these government military intelligence documents into a structured event data set. This is an example of a typical document on the bottom right. This is an intel report at the end of a week listing all of the events that happened that week. And when you put it in spreadsheet form, it looks like this. So every row is going to be a military event. Every column is going to be a feature we know about that event. So we have things like dates, locations, what type of event it was, perpetrators, targets, number of casualties, etc. We have much more columns than I'm presenting here that we're going to do a lot of future analysis with. But right now we're going to concentrate primarily on the where, the location information about these events. Now, these we got lucky because we decided to try to just capture everything we possibly could. So we told our coders to grab both military map coordinates when they saw it or textual descriptions, and they often did both. So we have for every event either a military map coordinate, which can be mapped to a latitude and longitude, or a natural language text explanation of a particular town, or maybe sometimes directions around a town. Unfortunately, we found that neither of those sources alone, neither of those types of location informations were sufficient by themselves. Only about half of our data have military coordinates. Another 35% of our data only have text explanations. And so we were left with kind of this problem. How are we going to recover latitude and longitudes for that portion of the data set that only have text? Fortunately, we also figured out this is kind of not just a cursing, but also a blessing. We have a subset of data that have both types, both military coordinates with an exact latitude and longitude, and a natural language text description. So any georeferencing strategy we come up with, we can benchmark and test against this known ground truth for the subset of our data that we can see both, and then use that to extrapolate and impute locations for the rest that we don't see. And that's the punchline of the experiments we'll be running today. To give you an empirical motivation, this is a very typical setup for a political science paper. On the left-hand side, we would want to predict the number of events that happen in a location, either the number of casualties or the number of total events or the number of rebel-initiated events, violence as an outcome of interest. On the right-hand side, we often have covariates that we have theories about. So you might want to put population on the right-hand side because you're interested in whether or not rebellions or civil wars are more concentrated in urban areas or in more rural areas. If you have economic theories about why civil wars happen, like over economic grievances, putting things like rainfall, which are a proxy for fertile land with good farming, are a way to get at those theories. There are theories about the ability for the government to project force. So the government often builds roads out into the boonies, into rural areas, so that its police and military forces can quickly get somewhere and put down a protest or put down a rebellion. So distance to roads might be a feature. Same reason, there are theories about rebel sanctuaries, like how mountainous or how many trees there are in an area give places for rebels to hide. So a very common regression you would see in a political science paper is to have violence on the left-hand side and covariates like these on the right-hand side, where the unit of analysis is some chunk of territory. We're going to do hexagon binning for this paper, but you can use anything you'd like. The first diagnostic we propose is checking whether or not location information is actually missing at random, or if the kinds of events that don't get coordinates are systematically different, right? I'm a lazy man. If these events are actually missing at random, I don't have to do anything else. I can run it on the subset that I have and go take a nap and not do any more work. The way we frame that is just a classification problem. On the left-hand side, we put a dichotomous yes or no. Did the event have a map coordinate? On the right-hand side, we put a bunch of things we know about each event. What document it came from, properties of the document, what properties of the event there were. We fit a classifier, in this case is XGBoost, and we find out that with 81% accuracy, we can predict whether an event's going to have a map coordinate or not. Not random, not even a little bit. And just to give you an example of some ways that it's not random, certain districts, this is going to be the district covariate here, certain districts are super likely to have their coordinates missing and just use textual explanations. Other districts are more likely to have coordinates. So this is a variation in military culture or bureaucratic culture. I often call this the institutional data generating process that happens before you ever get to the empirical data generating process you're actually interested in. We find that different parts of the war have different bureaucratic reporting practices, so certain years are more likely to give you coordinates than other ones. We find that the types of locations that are described are more or less likely to have coordinates. So if you're in a forest or you're in kind of a broader administrative area, you're less likely to get a coordinate. If you're a specific farm or in a state, you're more likely to get a coordinate. And the type of event also. So if it's a rebel getting captured, you're less likely to have a coordinate. If it's a specific theft, they're likely to put a coordinate. So if you just drop all the events and do no imputation, drop all the events that don't have actual latitude and longitudes attached to them, you're going to systematically study only part of the war in ways that will probably bias almost any question that you're interested in, right? So unfortunately, we have to keep working. There are a million decisions in a georeferencing pipeline. We concentrated on 4 big ones, and I'll discuss each one in detail, but briefly, they are which coordinate sources are you going to try to map your text to? Are you going to allow self-referencing, taking examples of events that have coordinates already and just extrapolating using the events data set only? Which geometry types are you going to allow? And what kind of string matching you're going to allow between text? And I'll discuss each of these here. The first decision is which gazetteer to use or which combination of gazetteers to use. For those of you who have never worked with this kind of data, gazetteers are just a list of place names, sometimes alternate names, and then the type of place it is, and then the latitude and longitude or some boundary polygon. We found over 13 different gazetteers that cover our area in Kenya. We looked at both contemporary ones today and historical ones that were created by the British military at the time or by the US military at the time. We looked at both publicly available ones, commercially available ones like Google API, Bing API, and also government sources. We looked at ones that were individual points with latitude and longitudes, but also ones that had polygons and lines. And we found that they are not created equal. Just wild variation. They cover different parts of the world differently. And this is part of the conversation we had yesterday about sources of bias in big data. Since we're in Africa, since we're in Kenya, the coverage is relatively poor because it's a historical case. The coverage is extremely poor for historical names. And we also found different levels of accuracy and sources of error across different gazetteers. And I'll just point out one fun one here. If you see this gazetteer here, you see these lines, these like strange lines. That's because it's rounding the latitude and longitude for a subset of kinds of places with no explanation anywhere for why that's there. So always plot your gazetteers, always rigorously interrogate it. Don't trust anyone's data ever. The next decision is to allow self-reference. I don't have much to say about this, but the idea here is that there's got to be some places. I have here the example of Bastard's Farm. SK Bastard Esquire, I'm not kidding, was an actual person in this area, had a big estate, and it shows up a number of different times in our events data, but nowhere in our gazetteers. So we had to ask ourselves, well, what are we going to do? And in some of those events, we got coordinates, exact coordinates. And so we wanted to know if it was cheating or if it was useful to just extrapolate that, create a gazetteer from the events data itself, and every time you see something related to Bastard, you just extrapolate and take those coordinates. One of the ways you can get in trouble with this is that there are multiple people from this family lineage, like this area of Kenya is full of bastards. And
that's not how that works.
So SW Bastard, SK Bastard, and so extrapolation can actually get you in trouble. It should be tested as a strategy. The third decision is which geometry type to use. So I've presented some earlier gazetteers that were all just points. These are examples of polygons, lines, things like rivers, roads. OpenStreetMap is a popular gazetteer source, and it has all sorts of strange structures with them, and how to handle those correctly is an open question. And the fourth decision is whether to use fuzzy or exact matching. Exact matching is where the toponym is just the name of a place. Exact matching is when a toponym matches verbatim to somewhere in a gazetteer source. You very rarely get that. It turns out fuzzy matching of toponyms is both a hard and unsolved problem, and here's just some slight motivation for why. I've cataloged just some of the problems that we discovered, and it's everything from personal names to near spellings that are matches, but near spellings that aren't matches, things with directions attached to the beginning or the end of the toponym, like 1 mile from where the water hole used to be. Synonyms, supranational information attached to the end, abbreviations, corporate names of businesses, compound locations, grid locations. It's a nightmare. It's an absolute nightmare. And so it's a very tough problem. I'm going to demonstrate just a little bit of the work we did on trying to solve fuzzy matching, which we're going to try to probably spin off into its own package and its own work. We treated it as a supervised learning problem. And we developed a training data set where our unit of analysis was a unique example in our event data set of a place name and the 10 that had a coordinate and the 10 closest gazetteer places nearby it. So these are all places that could have plausibly been a match. They're all in the neighborhood, but we only considered a match if, using our eyes, we saw the names were close enough that we considered it personally to be a match. We coded about 30,000 examples. We had on the left-hand side whether it was just a match or a no match. We then trained 2 classifiers, and it turned out we had to do this in stages because when you're comparing pairs from a large set, that squares quadratically in the number of items on your list, right? Because you have to compare every single 2 names, and that's computationally infeasible, especially for lots of features and even big classifiers like XGBoost. So what we did was we developed this first stage system where we generated just 1 feature for each toponym. We hashed it into 2-character n-grams. So A, B, B, C, D, E, counts of how many of those pairs that it had. And then we used something called locality sensitive hashing, which is a way of taking a feature like that, performing a function on it, a hash of it, where if 2 toponyms are close enough to each other on some metric, some cosine distance for us, if it was below like 0.3, the hash function would give them the same ID. And that's nice because you only have to go through the data set 1 time. You don't have to check every pair, you just have to hash everything once. And so what we were able to do is create this minimum floor that if 2 names are just wildly different from each other, like San Diego and Berkeley, and they hardly share anything, we can exclude them and we can weed out tons of pair comparisons that are just never going to be a match. Everything that survives that filter goes onto a second stage where we hit it with tons of features, all these different string distance measures, a fancy classifier like XGBoost, and we can rank each one by how likely it is to be a match. This worked fairly well for us. We were fairly happy with the results that we got out of this, which I'll talk a little bit more. And then finally, I've described different decisions that you have to make and different choices for each decision. But there's no reason you can't mix and match. And so we wanted to consider what would it look like to mix and match a couple different strategies. And we came up with 2 ways. One, if you're really fancy, treat this again like a supervised learning problem and try to learn what the best choice is every time you have multiple matches to pick from or no matches to pick from. And then a less fancy set of hand rules, just best practices. If you're really on a budget, you're doing it quickly, here are just some quick preferences, ways to rank order possible matches. The left-hand side here was the distance between a possible match and the ground truth, which we knew, in just log kilometers. And then we looked at all of the decisions that you can make, all the choices you can make, and tried to predict how far away a match was going to be from the known ground truth. And so using this method, you could go through, 10,000, 30,000 possible matches and predict how good a match it's going to be, and just always pick the one with the lowest distance as a strategy. When we tried to synthesize some hand-based rules from that, we had some rules that you might expect, like we always preferred exact matching to fuzzy matching. We always preferred points to polygons to lines. We actually liked self-matches quite a bit compared to no self-matches. And then we had a rank ordering of how much we liked each gazetteer source. This is all very specific to our country and our problem, so we're going to suggest ways in which you need to apply this to your own work and your own domain. But we were able to do it relatively easy. And I'm going to suggest 5 diagnostics for how to evaluate the quality of these decisions. One we already did, predictability of missingness. The second one is going to be the recall rate and the distance from an imputed location to the true known one. The third one is going to be the predictability of missingness, knowing things about the events. How weird are the ones that you impute given the details of the event. The next one is going to be bias on the covariates that I discussed earlier. How weird are your imputed locations relative to the known one in terms of things like ruggedness and terrain and things like that. And then the fifth one is just going to be, I'm going to run that real world regression that we described in the beginning and show how all the coefficients are affected by the different decisions. So here's the second diagnostic, recovery rate and the root mean squared error of distance. So on the y-axis, we have the recovery rate. This is the percentage of events that we were able to impute a location for. So higher is better. So the highest ones we had were about 0.7, 0.75 we were able to recover. The lowest ones were really poor, like 10% of events. And so what I have here is these are the decisions that we discussed earlier. Each name is an example of a choice that you could have made at that decision. And where they are on the scale, on the left-hand side is going to be how many events they were able to recover, and on the x-axis is going to be how close the imputed location turned out to be to the real known one for the subset we could compare the two. So you want to be in the top left, where you're relatively close to the true ground location, and you got a bunch of points recovered. You don't want to be in the bottom right, where you not only didn't recover many events, but when you did recover it, it was like miles and miles and miles away from where it was supposed to be. And just to give you some comparisons, like some concrete ones you can think about, like Google's API did relatively poorly. It had a decent recovery, but they tended to be really far away. OpenStreetMap, similarly, really far away, not so great recovery. Bing did worse than Google, but tended to be a little closer when it did get a match. Exact tended to be a lot closer than Fuzzy. Fuzzy had a little bit higher recovery for obvious reasons. Our ensemble method did really well. Both the ensemble and the handmade rules that we came up with, these had the highest recovery rate of everything because they're mix and matching. They're just trying everything they can. And they also had a decent distance from the true location. So we're able to get high recall and decent precision by combining strategies, whereas any individual one gives you some trade-off that's not great. The third diagnostic is going to be bias in outcomes, which is to say that in the same way we were worried about missingness not being random, we don't want imputation to not be random either. We don't want to be adding locations to a specific kind of event and skewing our analysis towards those kind of events. So we're going to keep recall on the y-axis here, just as before. But on the x-axis, we're going to put the predictability of missingness as a function of things we know about each event. So again, you want to be in the top left. You want high recall, and you want the kinds of events that you end up imputing to look more like everything else, not to be easily picked out. You don't want to be in the bottom right where you have low recall and it looks like you're obviously just imputing for a specific kind of event. And to be concrete about that, some of these here are biased really hard towards cities, right? If it's just a list of big cities and you use only that, then only events in big cities are going to get flagged. And what the classifier here is picking up on that and saying, hey, you're basically ignoring most of the war and you're only giving imputation to a specific kind of event, stop it. The fourth kind of diagnostic is going to be bias in the covariates. So we want to know if the kind of, as before, we want to know if the kind of point that a true coordinate exists at is going to be really similar to an imputed coordinate for that same location. And so I'm going to look at 4 covariates specifically, and I'm just going to break it down by different sources. So this one here, population, what 0 is going to be the baseline. This is for military coordinates. This is the 0 baseline. And then for every one of these, it's going to be the difference between how populous the point was that was imputed relative to what it should have been. And every single one of these sources is imputing a point that tends to be more urban, more populous than it's supposed to be. It's dragging it towards cities, it's dragging it towards population centers and away from the rural areas where the violence is actually happening. Same story for roads. It tends to be a little bit closer to roads for every source. Rainfall and ruggedness is kind of a mixed bag, but we found bias for every source and it points in different directions. So you can't even really sign the bias. You don't really know which direction it's pointing. And then I'm going to conclude with returning to that empirical motivation at the beginning, the regression. This is the thing we want to run. We already know that our strategies are going to drop certain kinds of events, so we're losing things on the left-hand side systematically, depending on our choice. We're also biasing all of our measurements on the right-hand side, which OLS can't just suck up in an error term. These are just going to be straight bias in your coefficients. And we're going to run the regression, and I'm going to, this is unreadable, but I'm going to zoom into it where on the y-axis we're going to have the p-values, and on the x-axis we're going to have the effect sizes, and you're going to get to see how those vary. So here's a good result. For population, this is the 0.01 statistical significance threshold here. It's always, no matter what strategy you pick, population is always significant. And the effect size and direction is pretty uniform. It's not too bad. Anywhere from about 1.3 to about 2 times more likely to have a violent event for every, I think it's 1,000 people we put on the right-hand side here. And our ensemble is kind of dead center, which is kind of what you hope to see, right? My guess would be the true effect is somewhere around here. So that's the good. Here's the bad. Rainfall is almost always significant, just one outlier here. But the effect size is anywhere from 9 times more likely to 30 times more likely. And this is, I think it's a number of events as a function of, I think it's like 100 millimeters per year. I forget what the measurement of rain here is. The substantive effect size is all over the place depending on what strategy you pick, which is bad if you're trying to substantively interpret your model and make suggestions based on it. Again, our ensemble is kind of down here towards the more moderate end, which I think is probably the right answer. Here's an example of statistical significance bouncing all over the place. So distance from roads, the effect size is always about the same, but half of these are above the threshold and half are below, which isn't great if you think p-values are the right way to think about relevance of a variable. And here's the ugly, where it's just all over the place. Ruggedness and tree cover, significant, non-significant, significant, non-significant, sign change, going the other direction. So now the decision you made way at the back of the statistical appendix and never talked about again is systematically giving you the opposite answer half the time, and you don't know when. So my takeaways are going to be georeferencing strategies aren't equally good and can and will change your downstream results. It matters. As a field, we need transparency and robustness checks for georeferencing strategies. It has to get into the same pipeline as every other robustness checks for statistical analysis. We got lucky and had a ground truth for our data set because of the military map codes. You may not. And so what we recommend is you need to at least ground truth a small sample of your data. I don't know how to do that. Interviews or other pieces of evidence, or people are using like crazy things like images that actually have geocoding to try to like prove people are at a certain place. Whatever it takes, try to get 100, try to get 200. It'll be painstaking, but it'll let you test these assumptions and know what's driving your downstream results. At least try to know and report the direction of your bias. You're never going to solve these problems. The bias is never going to go away, but you can at least know what it is. And if it points in the wrong direction or points in the right direction, you can be cognizant of that and report that when you interpret your results. Pick a gazetteer that's appropriate for your part of the world and time period. We found massive coverage differences. They're not all created equal. And don't just accept one solution. Combine a bunch of different solutions. We'll hopefully be releasing a package downstream that does that for you. Doing it by hand isn't too tough either. The handmade rules that we came up with were really easy to implement. Future work, I'm going to hopefully spin off the fuzzy toponym matcher as its own project. We're looking at additional features, like we were also using the big corpus of historical news from this time period. Initial experiments with that seemed to really overfit, and it seemed to hurt the predictive accuracy, so I still have a lot of tweaking with that. And finally, I'm hoping to replace the whole pipeline with a deep learning model. I have this working. It was still underperforming relative to just the simple XGBoost one that we developed. I think that putting an attention mechanism in and letting it pay attention to certain parts of toponyms is going to be the solution to that, but we have a lot more tweaking to do with that. And I'll stop there. Thank you.